perspective.
Exactly. It's a really powerful validation of quantum mechanics.
Right.
And what's even more amazing is that the Schrödinger equation doesn't just give us the allowed energies, it gives us the whole wave function, which tells us the shapes of these electron orbitals.
Okay, so we're talking about orbitals, those like regions of space where the electron is most likely to be found.
Exactly. And each orbital is labeled by these three quantum numbers, n, l, and m.
Okay, let's break those down. What do each of those quantum numbers represent?
So the principal quantum number n, that determines the energy level of the electron. It can be any positive integer, 1, 2, 3, and so on. And the higher the value of n, the higher the energy level, and on average, the farther the electron is from the proton.
So n is kind of like a ladder rung. Higher n means higher energy in a bigger orbital.
Exactly. And then we have the angular momentum quantum number, L, which can take on values from 0 up to n minus 1. And L determines the shape of the electron's orbital.
Okay, so different values of L give us different orbital shapes.
Precisely. So for example, L equals 0 corresponds to a spherical orbital. L equals 1 gives us a dumbbell-shaped orbital, and so on.
Okay.
And finally, we have the magnetic quantum number, M. And M can take on values from minus L to plus L, including 0. And M determines the orientation of the orbital in space.
Okay, so for a given L, M tells you how the orbital is tilted, so to speak.
That's a good way to think about it.
Okay, so those three numbers, N, L, and M, they give us this complete quantum address for the electron in the hydrogen atom.
Exactly.
And after we tackle the hydrogen atom, Griffiths takes us deeper into this concept of angular momentum.
Angular momentum, yeah.
You know, in classical physics, it's that measure of an object's rotation, like a spinning top or a planet orbiting the sun.
Right.
But of course, in the quantum world, things get a little more interesting.
They do, because just like everything else in quantum mechanics, angular momentum is quantized.
Okay, so it's like instead of a spinning top smoothly changing its speed, it can only spin at certain discrete rates.
You got it.
And it's those commutation relations again, right?
Exactly. The angular momentum operators have those special commutation relations that lead to this quantization.
Okay, so the values of angular momentum that a particle can have are restricted to these specific discrete values, just like the energy levels in the hydrogen atom.
Exactly.
And then things get even weirder. We encounter the concept of spin.
Ah, yes. Spin.
And this is where quantum mechanics really starts to depart from our classical intuitions.
It does.
Because electrons and other fundamental particles, they have this intrinsic angular momentum called spin, which isn't actually associated with any physical rotation.
Right. It's not like they're actually spinning like a top.
Right. So it's not really spinning.
Not in the classical sense. It's a purely quantum mechanical property.
Okay. But it's still a type of angular momentum.
It is. And just like orbital angular momentum, spin is also quantized.
Okay. So it's like a built-in angular momentum. It's just part of the particle's nature.
Exactly. And for electrons, spin can only take on two values. We call them spin up and spin down.
Okay.
And we denote those by plus h bar over 2 and minus h bar over 2, where h bar is Planck's constant divided by 2.
Okay, so it's like the electron has this tiny little arrow, and it can point either up or down.
That's a good analogy.
And this quantization of spin was experimentally demonstrated in that famous Stern-Gerlach experiment.
Right, where they sent a beam of silver atoms through a non-uniform magnetic field.
Okay.
And classically, you expect the beam to be deflected continuously, but what they found was that it splits into two distinct beams,
Okay.
corresponding to those two spin states of the electron.
Wow. That's a pretty clear demonstration that spin is real and it's quantized. So how do we represent spin mathematically?
We use things called spinors.
Spinors. Are those like vectors?
They're similar to vectors, but they actually live in this two-dimensional complex vector space. And each spinor has two components, one for spin up and one for spin down.
Okay, so the spinor encodes all the information about the particle's spin state.
Exactly. And we can use spin operators to act on these spinors.
Okay, so it's like those operators we talked about for position, momentum, and angular momentum.
Exactly.
And do these spin operators also have those special commutation relations?
They do. And the commutation relations for spin operators are actually identical to those for orbital angular momentum operator.
Okay, so even though spin is this completely quantum mechanical property, it still sort of follows the same mathematical rules as angular momentum.
Exactly.
That's pretty cool.
It is.
All right, so that wraps up Chapter 4, our journey into the 3D world of quantum mechanics.
We've covered a lot.
We have. We've encountered all sorts of mind-blowing concepts, the quantization of energy, the quantization of angular momentum, this strange thing called spin. It's amazing to see how the math is describing this completely different reality at the atomic level.
It is.
And now, get ready for the final frontier. We're boldly going into the world of identical particles in Chapter 5.
This is where quantum mechanics starts to get really, really weird.
Okay, I'm intrigued.
Yeah.
Okay, so we're talking about particles that are like completely indistinguishable from each other.
Exactly.
Okay, so let's start with the simplest case, two particle systems.
Right. So when we have two particles, our wave function now depends on the coordinates of both particles.
Okay, so it's like we've gone up a dimension. Instead of a wave function in 3D space, we now have a wave function in 6D space.
Exactly. And this is where things start to get really interesting. If those two particles are identical, they have the same mass, same charge, same spin, everything, then we can't actually tell them apart.
Wait, hold on. We can't tell which particle is which. How is that even possible?
It's one of the most mind-blowing things about quantum mechanics. This indistinguishability of identical particles is a fundamental principle.
Okay, so we're not just saying it's really hard to tell them apart. We're saying it's fundamentally impossible.
Exactly. It's like, imagine you have two electrons. You can't just label one A and the other B and follow them around individually. They're fundamentally interchangeable.
Okay, so this indistinguishability, it really throws a wrench in how we describe these systems, right? Because our usual way of thinking about particles as having individual identities, it just breaks down.
It does. And it has huge implications for how we construct the wave function for a system of identical particles. Because the wave function has to have a very specific symmetry.
Okay, symmetry. We've encountered that before.
Right.
So what kind of symmetry are we talking about here?
Well, the wave function for a system of two identical particles, it has to be either symmetric or antisymmetric when we swap the labels of the two particles.
Okay, so symmetric means if we swap the labels, the wave function stays exactly the same.
Exactly. It's like looking in a mirror. The image is flipped, but it's fundamentally the same image.
Right, okay, and antisymmetric means?
Antisymmetric means if we swap the labels, the wave function picks up a minus sign.
Okay, so one stays the same, the other one flips its sign.
Exactly.
Okay, but why is this distinction so important?
Because this seemingly simple difference in symmetry, it leads to one of the most fundamental divisions in the quantum world.
Okay, what's that?
Bosons and fermions.
Yes. Bosons and fermions. Those terms always come up in physics.
Yeah.
So what's the connection between this symmetry and bosons and fermions?
Well, bosons are particles with integer spin, like 0, 1, or 2, and their wave functions are symmetric under exchange.
Okay.
Fermions, on the other hand, they have half integer spin, like 12 or 32, and their wave functions are antisymmetric.
Okay, so the spin of the particle dictates which club it belongs to, boson or fermion.
Exactly. It's like a quantum ID card.
Okay, so can you give us some examples of these quantum celebrities, bosons and fermions?
Sure. Photons, which are the particles of light, those are bosons.
Okay.
They have a spin of 1. Electrons, protons, neutrons, those are all fermions.
Right.
They have a spin of 12.
Okay, so some pretty important players in the universe fall into these two categories. Now, this difference in symmetry, symmetric for bosons and antisymmetric for fermions, does that actually have any real-world consequences?
Oh, absolutely.
Okay, like what?
Well, one of the most profound consequences is the Pauli exclusion principle, which applies to fermions.
Ah, yes. The Pauli exclusion principle? I remember learning about that.
Yeah.
It says that no two fermions can occupy the same quantum state at the same time, right?
Exactly.
Like they need their own personal space.
That's a great way to put it. And it's a direct consequence of the antisymmetry of the fermionic wave function.
Right.
And this principle is crucial for understanding the stability of matter, the structure of atoms, the whole periodic table of elements.
Wow. So this abstract concept of wave function symmetry is actually responsible for, like, the very structure of the world around us.
It is.
Okay.
To illustrate this, Griffiths considers two non-interacting particles in the infinite square well.
Okay. So we're back to the quantum billiards table.
We are. So imagine we have two particles bouncing around inside this box.
Okay.
Now, what happens if those particles are identical bosons? Well, if they're bosons, their wave function has to be symmetric.
Right.
But if we try to put both of those bosons in the lowest energy state, the ground state of the well, something weird happens.
What happens?
The wave function becomes 0 everywhere. It's like the universe is saying, nope, that's not allowed.
Okay.
But it's not that they can't be in the same state.
Hmm.
Bosons love to be in the same state.
Okay.
They're not subject to the Pauli exclusion principle.
So they're like social butterflies,
Exactly.
happy to mingle in the same quantum state.
Exactly.
But fermions are more like people who need their personal space.
That's a great way to think about it.
They can't be in the same state.
Exactly. And that has profound implications for how matter is structured. It's why the electrons in an atom, they can't all just crowd into the lowest energy level.
Right. They have to spread out. They have to occupy different orbitals, which leads to this beautiful complexity of atoms and all the different elements that we see.
Exactly. It's all thanks to the Pauli exclusion principle.
Wow. Okay, so we've covered bosons, fermions, the amazing consequences of this exchange symmetry.
Yeah.
What else does Griffiths explore in this chapter?
Well, from there, he goes on to look at atoms, which, of course, those are multi-particle systems consisting of those electrons bound to a nucleus.
Right, so we're taking a step toward more realistic systems.
Exactly. And the key point here is that the Pauli exclusion principle is what dictates how the electrons fill up those energy levels in an atom.
Okay.
So the electrons can't all just pile into the lowest energy level because they're fermions.
Right.
They have to spread out. They have to occupy different orbitals, which is what gives rise to the shell structure of atoms. And it explains, the whole periodic table of elements.
So it's like the Pauli exclusion principle is the architect of the periodic table.
You could say that.
It determines how many electrons can fit into each shell, which then determines all the chemical properties of each element.
Exactly.
Okay.
And from atoms, Griffiths extends the discussion to solids, which are basically, giant lattices of atoms.
Okay, solid. So we're talking about metals, insulators, semiconductors. How does quantum mechanics play a role in understanding their behavior?
Well, it all comes down to the behavior of those electrons in those solids.
Okay.
Whether a material is a good conductor, an insulator, or somewhere in between, that depends on how the electrons are arranged and how they can move around within that lattice.
So it's like those tiny little electrons, governed by these quantum rules, are ultimately determining whether a material will conduct electricity or not. That's incredible.
It is. And quantum mechanics gives us the tools to actually understand those behaviors,
Right.
and even predict them and design new materials with specific properties.
So we've gone from like single particles and these idealized potentials to understanding the behavior of macroscopic objects.
We have.
That's pretty amazing.
It really shows you the power and the reach of quantum mechanics.
It does. Okay, so to wrap up Chapter 5, we get a glimpse into this thing called quantum statistical mechanics.
Yes. Quantum statistical mechanics. It's a really powerful framework for understanding systems with many identical particles.
Okay, like a gas of atoms or a bunch of electrons in a solid.
Exactly. So in classical statistical mechanics, we deal with probabilities of particles being in different states. But in the quantum world, we have to take into account this whole idea of indistinguishability.
Right. We can't just treat them as individual billiard balls anymore.
Exactly.
They're all blurry and mixed up.
Exactly. And that leads to some different statistical distributions, for bosons and fermions.
Okay, so even in statistics, bosons and fermions are playing by different rules.
They are.
Can you give us an example of how these differences actually manifest?
Sure. One of the most striking examples for bosons is this thing called Bose-Einstein condensation.
Okay.
It's where at really, really low temperatures, bosons can all just crowd into the lowest energy state.
Okay.
They form this sort of superatom where they all behave as one.
So it's like all those blurry, indistinguishable bosons decide to throw a quantum party and all pile into the same state.
That's a great way to put it. And this phenomenon has actually been observed in labs, where atoms are behaving like this single macroscopic quantum object.
That's wild. And what about fermions? Do they have any cool statistical tricks?
They do. Fermions follow what's called the Fermi-Dirac distribution.
Okay.
And that's actually responsible for the stability of matter.
Okay.
It's this distribution that prevents all the electrons in a metal from collapsing into the lowest energy state.
Right, because the Pauli exclusion principle is like, nope, you each need your own quantum space.
Exactly. So even in the world of statistics, quantum mechanics is calling the shots.
It's amazing how it all ties together.
It is.
All right. Well, that wraps up Chapter 5, our exploration of this mind-bending world of identical particles.
We've learned a lot.
We have. We started with this weird concept of the wave function. We explored the strangeness of the uncertainty principle. We delved into the elegant formalism of Hilbert space and operators. We uncovered the secrets of the hydrogen atom, and then we navigated this, like, totally counterintuitive world of identical particles.
If
Feel like we've got a pretty good grasp on quantum mechanics now.
you're well on your way to becoming a quantum mechanic.
Yeah.
And the good news is we've only just begun.
Okay.
Because in part 2 of Griffiths' book, we're going to be exploring even more advanced topics, and we'll start to see how these quantum principles are actually applied in all sorts of different fields, from, atomic and nuclear physics to solid-state physics and even beyond.
I can't wait to see how all this quantum magic plays out in the real world.
It's going to be exciting.
All right, we're back and ready to wrap up our deep dive into Griffiths' introduction to quantum mechanics.
Yeah, we've covered a lot of ground in the first 2 parts. But this last part, this is where we really start to see the power of quantum mechanics in action,
Yeah, I'm excited to see how it all comes together. So, Chapter 6 introduces us to this thing called time-independent perturbation theory.
Right. This is a really clever technique for dealing with problems that are just too complicated to solve exactly, which, let's face it, is most problems in the real world.
So is it kind of like admitting defeat, saying, okay, this problem is too hard, let's just find a way to get a good approximation?
Not really. It's more like saying, let's start with a problem that we can solve exactly, and then let's see how a small change or perturbation affects that solution.
Okay, so we start with something we understand, and then we kind of nudge it a little bit and see what happens.
Exactly.
And perturbation theory gives us a way to systematically calculate how that nudge affects the system's energy levels and wave functions.
Precisely.
Can you give us an example of how this might be used in the real world?
Sure. Imagine you have an atom sitting in an electric field.
Okay.
That electric field will slightly distort the electron cloud of the atom, and that'll shift its energy levels a little bit.
So it's like the electric field is kind of poking the atom and making it wobble a bit.
That's a great way to think about it. And we can use perturbation theory to calculate exactly how much those energy levels shift.
Now, Griffiths distinguishes between non-degenerate and degenerate perturbation theory. What's the difference?
Well, it all comes down to the energy levels of the system. In non-degenerate perturbation theory, all those energy levels are distinct. They're all nicely spaced out.
Okay.
But in degenerate perturbation theory, we have 2 or more energy levels that have the same energy.
Okay, so it's like having, multiple apartments on the same floor of a building.
Exactly.
Okay.
And when we have those degenerate energy levels, things get a little more complicated mathematically. We need a slightly different approach.
So degenerate perturbation theory is like a special tool for handling those cases where the energy levels are kind of overlapping.
Precisely.
Okay. Now, one of the coolest applications of perturbation theory that Griffiths discusses is this thing called the fine structure of hydrogen.
Ah, yes, the fine structure. This is where we start to get into the really nitty-gritty details of the hydrogen atom.
Okay, so we're going beyond that basic model that we learned about earlier
Right.
and taking into account some more subtle effects.
Exactly. And the fine structure, it refers to these tiny, tiny shifts and splittings in the energy levels of hydrogen. Shifts that aren't predicted by that simple Bohr model.
Okay.
And those tiny shifts, they're actually due to things like relativistic effects.
Yeah.
The electron is moving pretty fast around the proton, a significant fraction of the speed of light.
Right.
And there's this interaction between the electron's spin and its orbital angular momentum.
Okay, so we're starting to see how all these different concepts that we've been learning about, relativity, spin, angular momentum, they all kind of come together.
They do, and perturbation theory allows us to calculate those shifts and splittings incredibly accurately. It's really a remarkable demonstration of the power of quantum mechanics to explain these really minute details of atomic structure.
Yeah, it's amazing. Now, Griffiths also mentioned something called the Zeeman effect.
What is that?
The Zeeman effect, it describes what happens to those atomic energy levels when we apply an external magnetic field.
Okay.
It's like the magnetic field is perturbing the atom, causing those energy levels to split.
So it's similar to the Stark effect, but with a magnetic field instead of an electric field.
Exactly. And again, we can use perturbation theory to calculate those splittings really, really precisely.
So perturbation theory is clearly a really powerful tool for analyzing all sorts of phenomena, the Stark effect, the Zeeman effect, the fine structure of hydrogen.
It is.
It's amazing how far it can take us. Okay, so what's next in our quantum adventure?
Well, Chapter 7 introduces us to this thing called the variational principle.
Okay, the variational principle, what's that all about?
It's another really useful technique for getting approximate solutions to the Schrödinger equation. And it's particularly helpful for dealing with systems that are too complex to solve exactly, even with perturbation theory.
Okay, so it's like a whole different approach.
Yeah.
Yeah. The variational principle, it basically says, let's guess the ground state wave function of the system.
Wait, hold on. We just guessed the wave function.
Well, it's more like an educated guess. We choose a function that we think might resemble the true ground state wave function, and we call that a trial wave function.